Okay, almost done.
Almost done.
Last speaker is Lorenzo Calibbi, and again, some other ideas about heavy scales of new physics and beyond the TeV, this time from flavor. Maybe the opposite of what you were saying.
Okay, thank you. Good afternoon. And thanks to Dario and Roberto for the invitation. Well, in my case, actually, the title I was assigned is easier and less crazy than other speakers because, I mean, flavor obviously point to beyond the TeV. So I didn't need to invent anything really exotic to connect the two keywords, okay? Flavor and beyond TeV scale. So let me just start with the usual motivation why flavor physics is interesting, why flavor physics has been studied for a long time, and why I think we should keep working on that. And well, my opinion, the obvious reason is that the standard model, the flavor sector in the standard model in itself is not very well understood, or at least there is something we don't know about it, or we cannot explain about it, starting from the very simple fact that there are three families, three generations of fermions. And we live here, as you know, and we don't know why there are other two fermion generations and why there are three altogether. And we observe a peculiar hierarchy patterns of the masses of fermions. And again, it could be an accident of nature, or it could be a hint of something more fundamental. We don't know, but it's interesting to ask ourselves if we can learn something from this. And so basically, the question, or what people may call the standard model flavor puzzle, is related to the fact that in the standard model, the flavor sector is not robust. There are many free parameters. You can use them to fit the data, but it's kind of loose. So it lacks a fundamental principle, like the gauge principle, that gives you the gauge interaction just in terms of the gauge couplings. Nothing like that exists in the flavor sector. We can fit things, but we have to put if you want, the values of these Yukawa couplings by hand. And what we observe in terms of masses and mixing does not look like generic at all, okay? Especially in the core sector, you have this hierarchical structure in the CKM matrix in the core, for instance. So it's legitimate to ask ourselves if there is some fundamental, some new dynamics behind these patterns. And so flavor physics is important, not only in itself, because we don't really have full control, let's say, of the standard model flavor sector, but also because we don't know. We know that there is new physics somewhere, but now we don't know the scale, okay? So flavor observables are a good way to access a scale, to try to test scales that are beyond, even beyond what we can directly test at colliders. And if you remind ourselves why we believe that there is some new physics out there, of all the usual stories, many of them actually are in principle testable with flavor violating observables, CP violation, and so on. Marcus mentioned yesterday that in general, if you have TeV scale new physics, you mess with the flavor sector, you induce new sources of flavor violation, unless you have a theory it is very well protected against flavor changing neutral currents, like what Giovanni just showed us. But in general, no, if you want to address the things we don't know, you extend your the theory, and especially in the lepton sector, I would say, you introduce new sources of flavor violation, of CP violation. So it's not inconceivable that you can test these ideas through flavor observables. So we get to famous plots like this, right? That gives you the present bounds in terms of the energy scale associated to dimension 6 effective operators that induce certain flavor observables. That gives you the present constraints, the future constraints. Here you see we have meson observables, lepton flavor violating decays, also flavor conserving stuff like EDMs, Higgs, top. And again, one shows this kind of plot because you see that this energy scale, in principle, is very high. It can reach way beyond the TeV level. Or in other words, if there is any new physics at 1 TeV or 10 TeV, you need the couplings, the mixing angles to be very small, so to suppress this, if you want, these dimensionless numbers here, okay? So to allow your new physics contribution to be consistent with the stringent constraints from flavor observables. And what we have been learning during this workshop, so the connection with Mu Collider is interesting because some of these operators can be tested in a different way. Of course, at the Mu Collider, of course, you need to muons to be involved, so operators that are, let's say, some muon-philic new physics. But in such a case, if you, instead of looking, say, of a B sub S decaying into mu plus, mu minus, you can directly search for mu plus, mu minus collision, giving you a B and a strange in the final state. And in certain cases, like this one, a 10 TeV muon collider could give a better sensitivity to the same operator, if you want, so to the same new physics, the same microscopic new dynamics that would give you a new physics contribution to the rare BDK. You could test it directly at high energies, obtaining a better sensitivity. So there is this nice interplay. So you can do, in a way, flavor physics with muon colliders too, simply not through flavor observables in a way, but you can access the same kind of new physics. So now, this was just a generic introduction. Now I come also to a short parenthesis where, since we're talking about high scales, and at the same time I mentioned that the standard model flavor sector is puzzling in itself, I discuss what is the silliest, probably, anyway, the simplest way to address the standard model flavor puzzle and how you can test that, okay? It dates back to 79, so it's almost as old as myself. And so basically the idea is to explain why you have small numbers, so small Yukawa couplings, so why the up quark mass is much lighter than the top quark mass through high dimensional operators. So you introduce a new symmetry, a symmetry of flavor that forbids the Yukawa coupling, so forbids fermion masses, which then arise as higher dimensional operators through after the spontaneous breaking of this asymmetry. So basically, you will have some new scalar, a sort of flavored Higgs, field that breaks this asymmetry of flavor, and then your Yukawa interaction arises like a higher dimensional operator like this, with a certain number of insertions of this flavor breaking VEV, which then will give you a dependence on this ratio. So it's enough to assume that the VEV of this scalar is somewhat smaller than the cutoff, and then you will get small numbers. And these exponents are dictated by the symmetry, okay? Because if you want, these operators need to be invariant under the under the flavor symmetry. So choosing the representations, the charges of your standard model fermions under the flavor symmetry, you can explain these patterns here, okay? Simply, you need, for instance, larger charges. If you are thinking about of an abelian symmetry, like a U1, you need larger charges for first generations, then second generation and third generation. So you have larger numbers here, okay, larger exponents here, and you suppress the Yukawa couplings. So this is the basic idea. In principle, it's very simple and beautiful. Then the realizations have all their problems. But what I like of it is that in general it's generic, because so far I didn't tell you what is this symmetry. No? It could be discrete or continuous, abelian, non-abelian, local, global. So all possibilities are open. So now I just give you the simplest, which was, by the way, the original proposal by Frog and Nielsen. So you just have a new charge, a new flavor charge, a new U1. You charge your 3 generations. So it's a, if you want, flavor non-universal horizontal symmetry, okay? The 3 generations are, you distinguish them, giving them, assigning to them different charges under this flavor symmetry. So you can just choose these charges, and then you, from this kind of operators, you obtain a pattern of your Yukawa matrices that can then fit the observed fermion masses and mixing. It's not a very predictive theory, because here in front of these operators you have, in principle, as many coefficients as the Yukawa couplings themselves, okay? So order 1, that you assume to be order 1 coefficients, and they're what they are related to the fundamental couplings, the Yukawa couplings in the UE. So of course, if you want to UV complete this, you have to open this blob, add some heavy fields that will live at this scale lambda, like vector-like quarks or heavy scalars. So all these couplings between these messenger fields, so-called, these flavon fields, the light fermions, and so on, the products of these fundamental couplings will enter here and give you this coefficient. We assume them to be order 1 because we want that the hierarchies are only generated by the mechanism itself, not by peculiar choices of this, okay? But we don't know what they are, so we don't have control unless you really write a super UV complete theory, but it would be a little bit complicated. But of course, you can fit them against the data. Simply, there are many more than the constraints, than the masses and mixing. So they will introduce uncertainties, let's say. So whatever I can tell you about this kind of models, at least if I try to be generic, not specify not engaging in a very detailed model building, is like order of magnitude estimates, let's say. So whatever bounds I show will be dependent of order 1 uncertainties, let's say. Anyway, what I want to do now is to take this U1 and make it local, which is, of course, this example of charge assignment is anomalous, but people have shown that one can write UV completions that basically automatically make it so. Playing with these messengers at the scale lambda that I mentioned, you can make automatically the theory anomaly-free, this U1 anomaly-free, or you can even imagine that the anomalies are taken care of in some dark sector or whatever. So for the moment, again, I'm not specifying the model too much. And I imagine that this is a local U1, so you have a Z prime, okay? So you have a gauge boson, which is by construction flavor violating. Because as I mentioned, and I'm showing here, if you want to explain why the up quark is lighter than the charm quark, the two need to be to have different charges. So they have different charges, so they couple to this the Z prime with different strengths. And then when you rotate, so when you rotate your Yukawa matrices to work in the mass basis, in the fermion mass basis, then this rotation will appear here in the interactions of the Z prime and off-diagonal terms, okay, flavor-violating terms arise. So basically, this is a Z prime that can convert, like in this example, a strange quark into a down quark, okay? So it mediates flavor change with neutral currents at the tree level, okay? So you can have processes like this. So tree-level exchange that gives you constraint from K-bar mixing. So you see, the couplings, of course, is proportional to this GF, which is the new gauge coupling. So, sorry, the flavor gauge coupling, the gauge coupling of this local U1. And you exchange the Z prime, which, of course, whose mass is also related to this G times the VEV that breaks the symmetry. So you see this G squared actually cancel, and these kind of processes are only sensitive to the VEV of the scalar, so to the scale where you break the flavor symmetry. Then, if you pay the price of a small g, okay, why not? The mass of the Z prime is much smaller than the flavor breaking scale. And if it is really small, so you can kinematically open things like this, okay? So you can, the Z prime is lighter than B quarks. So in this case, you not only mediates processes of this kind, but actually mesons or leptons can decay into it, okay? So this gives another set of constraints, if you want. Really decays of standard model particle into on-shell light, new light gauge bosons, okay? Yes, I do. But I'm considering both possibilities, let's put it like that. Maybe I can introduce another U1 that Frogan-Nielsen down at the G. Good point, anyway. Anyway, I'm not committed to anything. I just show you this G from 1 to a crazy small number, no? And I want just to set the constraints, okay? Of course, if G is large enough, the only thing, the main bound is K-bar mixing, okay? So I don't know if there is any new CP phase here. Here there is not, but it also depends on the on these rotations here, okay, which depends on those unknown order 1 coefficients and so on. So if I want to be conservative, I only impose the bound from delta m k, so the mass difference between the kaon mass eigenstates. And this gives me the minimal bound, if you want. So I know that the scale, the flavor breaking scale, cannot be smaller than order 10 to the 6 GeV, okay? So already flavor constraints are pretty strong. Then, of course, if I play this tuning game, I made the gauge coupling to smaller and let kaons decay into it. Then the bound from K to pi and this light state, then depending on this lifetime, it will be a bound from K to pi invisible, or a bound from K to pi and the Z prime decaying inside the detector into mu plus mu minus, for instance. But considering both cases, okay, visible and invisible Z prime decays, basically what you get is that the scale needs to be much, much larger, okay? So the lower bound is order 10 to the 11 GeV. Of course, the bound is stronger if you have some light state. Your standard model particles can decay into. And by the way, if this is global, so I don't play any G prime, you have a pseudo-Goldstone boson, okay? So the bound will be the same. So it will be the K, the bound from K to pi plus axial-like particle, it will be the same. You know, there is an equivalence theorem or something. Roberto? As? No, okay, but I mean, I just stop plotting, okay? But I can go up. Simply, then the G at a certain point will reach 1, and then maybe I can stop there. Actually, I have it here, okay? Yeah, the bound is much stronger because kaons can decay into it. That's it. Yeah, yeah. Or if you want, which corresponds to have a flavor breaking scale about 10 to the 11. No, because you see, mz prime and the scale are related, right? I mean, these three parameters, yeah, you have just two free parameters. So here I'm taking mz prime and g as a free parameter, so then I get the scale. What Giovanni said, that I completely agree. Simply here I'm just showing you the full range. Okay, this is just one single parameter, okay? While, you know, you trade many small number for just one. I don't know if it is an improvement or not, okay? I mean, I'm not committed to this model. I want just to show you small numbers, large scales, and especially I want to show you this, actually. This was the fun game, gravitational waves, because you have a U1, right? Spontaneously broken at some high energy. So you will have a phase transition. I mean, the only assumption is the heating temperature is larger than Vf, the scale. If it is, in the early universe, we had a phase which is flavor symmetry conserving, right? Temperature drops. Universe undergoes a phase transition. You don't need to assume anything dramatic. A simple second order phase transition would do the job. But you produce cosmic strings. And then the cosmic string network will evolve and so on. No, they will form loops and stuff and will emit gravitational waves, as usual, producing stochastic gravitational waves background, which gives you a signal which is stronger for larger scales, for larger flavor breaking scales, because the tension of the string is proportional to this VEV and so on. So this is a very simple exercise. So these gravitational waves from a local U1 is not different from any other model, but in this context it's fun to see, because here I can exclude in gray this thing that comes from flavor, right? The flavor bounds. So flavor test like low to intermediate scale flavor breaking, while future gravitational wave observatories will come from below in this plot, no? So it will sandwich this model, leaving eventually maybe just this strip untested. Okay, so it's the complementarity, the interplay with flavor that tests scales up to 10 to the 6 GV, or if you are very lucky, 10 to the 10, whatever, if you are here. and gravitational waves that test scales which are above a certain threshold. Now, this complementarity is fun also because it closes the parameter space here, especially in the part that we like the least. You also bounce from BBN because this thing then will start being kind of long-lived, decay after BBN. Exactly. Well, yeah, forecast from, well, whatever you can hope to have in the future, Einstein, telescope, LISA. You start producing stuff, yeah. No, now we consider this effect of having, if I understand what you're mentioning, a fat string, and this kind of cut off the signal at high frequency or something like that. But still, this is why, this I don't remember. But for instance, you see, if you don't consider the effect you mentioned, for instance, BBO would reach this dashed line, all this, yeah, decrease in sensitivity is precisely because of this effect. Yes. Yeah. Yeah. So so you say this, you have an enhancement, the signal should increase. Mm. So maybe we are conservative here. So maybe we are, yeah. So maybe we are conservative here, and we could get a. Now we can discuss anyway. So you see, I mean, the exercise is to compare the reach of two, and I mean the outcome is kind of fun. How much time do I have? 20 minutes or something? Okay, so this was basically well, the introduction plus showing you this interplay and these very high scales that still these are high scale related to flavor somehow, but in principle you can test them also not with flavor observable, but with gravitational waves under a certain number of assumptions. But now I want to do something completely different and talk about future colliders, okay? And I want actually to focus on CPC, FCC, working as TeV factory, okay? So high energy plus and minus, running at the Z pole and producing a lot of Z bosons, okay? As you know, the two projects are kind of equivalent for what concerns the physics outputs, so I will focus on the CPC, not only because I work in China, but also because I was part in writing this document, okay? So it's a white paper on the flavor prospect of the CPC, especially on the Z pole run of the CPC. And you can find it here if you're interested. So we consider reviewed a lot of possible flavor searches you can do at this kind of machine. So there are many options. So now I will just give you some highlights based on, so by far not complete, just based on what I like the most. So you know the idea, again, here I'm using CPC as benchmark. The idea is that besides producing Higgs, you can run at the Z pole, and this will give you basically more than 10 to the 12 visible Z decays. Okay, so that's why they call it TeV factories. And you know that if you have 10 to the 12 Z, and you look at the branching ratios of the Z into fermions, you will have more than 10 to the 11 heavy quarks, so heavy flavor pairs, particular BB bar, CC bar, tau plus, tau minus, okay? So you can see the number of B mesons, for instance, that you can produce running at the Z pole compared with Bell 2 and LACB. Some things Bell 2 cannot have just because of energy, like B baryons. So in general, the yield of a tera Z is larger than Bell 2, even considering the all Bell 2 lifetime, the promised integrated luminosity of 50 inverse aptoban, and is much smaller than LACB, but of course, in a much cleaner environment, okay? So why then it's a good idea to use a tera Z factory to do flavor study, so flavor factory. So the luminosity is the first reason, what I just mentioned, okay? You have order 10 to the 11 heavy flavor pairs. And then there is also energy, I already mentioned. So there are some states you cannot produce a Bell 2. And also, you are producing boosted objects compared to Bell 2, okay? So this surplus energy that you have, since the BB bar and the others are produced in Z decay, will give you a longer decay length, so it's easier to track, no? To tag, the vertex reconstruction uncertainty is smaller, and so on. And then, of course, it's not a hadronic machine, so it's clean. So they can do things that LACB, unfortunately, cannot. Also, I mean, the kinematic constraints are more powerful because you know the initial state, right? So when you impose the invariant, the constraint from the invariant mass of your decaying, of your product that should match the Z mass, then you are just limited basically by the Z width. No, sorry, by the uncertainty of the energy beams, not by the Z width. Anyway, so it's a clean environment, so this helps you, this allows you to see things that to search for things that cannot be searched for in a hadronic collider, so involving neutral particles, invisible particles, neutrinos, or light, invisible new physics particles, and so on, okay? So one can search for many things. I will give you basically just a few examples that highlight the advantages of this kind of machine with respect to these two. So in a way, they are cherry-picked to leverage these advantages, okay? So something that you cannot do easily at Bell 2 or LACB. So things involving neutral particles, taus, things that are more difficult at other flavor factories. So one is this, so processes of the kind B2S, tau plus, tau minus. We know fairly precisely what is the standard model prediction of them, and we never observe them. So the present bounds, the present limits are a few orders of magnitude away from the standard model prediction, and you cannot expect Bell 2 to give more than one order of magnitude increase, okay? On the other hand, you can imagine that if new physics couples preferably to third generation, this will be enhanced with respect to the standard model. So there was this study, they considered to tag the two taus, so to take three-prong decay. So anyway, you have a lot of taus. You both of them you consider decays into 3 charged particles, or 3 pions. And doing like that, they claim that if this is the sensitivity of Bell 2, a TeV factory can get around here, okay? So below 10 to the minus 6 level for a number of processes of this kind. So not far from what is the standard model prediction. I guess this is purely statistically based. So I don't know if including a serious study of the systematics, this prediction is very robust, but this is what we have at the moment. And then if you translate it in a bound on the low energy effective theory operator, as usual normalized in this funny way, you get this, that then if I translate it in a way I can understand, so just in terms of the scale of new physics, this gives you sensitivity order 10 TeV or something, okay? Which is typical when you look at this kind of observables. Same as this, but with neutrinos. So again, now we have a final neutral final state. So this is difficult, impossible at LACB, for instance. And you know that we just had evidence from Bell 2 on one decay of this kind, B2K in Unubar, so a 3 sigma evidence. And so the idea is, again, these kind of things could be announced by new physics, especially lepton flavor non-universal new physics, usually scenarios, models that were introduced to fit, to explain the now dead flavor anomalies, but nevertheless, people studied also in the concept of FCC what kind of precision a TeV machine can have on observables of this kind, and they claim they could measure it. Okay, this is the standard model prediction. It's about 1 order of magnitude besides this, below the present bounds, and the TeV factory could reach, could measure the processes, even if there is no new physics contribution, purely standard model, with percent level precision. Okay, so this is the outcome of these papers here. Again, B physics, but this time a charge current process, which is of the same kind as that would that is tested by the famous RD star observable. So B sub c to tau nu. It's also a way to directly measure the VCB angle of the CKM. So again, here they studied and think that a percent level measurement is possible. Okay. This is a 3-level process in the standard model. So the Prandtl ratio is large, it's 2%. But I mean, there is a tau and there is a neutrino. So this is impossible at the LACB. And a B sub c is too heavy for Bell 2. So again, this is something that only using the high energy and the clean environment of any plus or minus collider at the z-pole could be studied. For those who were here last week, I already showed this slide. Of course, you have a Z factory, so you can also look for lepton flavor violating Z decays. The expectation is that there will be several order of magnitude improvement with respect to the current limits and whatever a high luminal LHC could do because of the background that they have from Z to tau plus, tau minus. The question is, any operator you introduce that gives you lepton flavor relating Z decay would also induce some lepton flavor violating process involving so some lepton flavor violating tau or muon decay. Because an effective flavor violating coupling of the Z can be used with the Z exchange also to induce a tau decay, for instance. So you can compare the sensitivity of searching for this at the Z factory and searching for the corresponding tau decays at the Bell, so at B factories in the past, and in the future, this light colored histogram at Bell 2. And you see that there is a complementarity, okay? So especially if Bell 2 is not going to reach the 50 inverse Aptovan, there is possibility of testing some new physics with these ZDKs up to scales of the 20 or 30 TeV. RD star is same kind of microscopic interaction we were talking about before. So 3-level in the standard model, and is a test of lepton flavor universality. As you know, it's something that has been going on for a long time. The current precision of these ratios is order 5–10%. The world average is still somehow out in tension with the standard model, but it's getting more and more standard, I would say. Okay, but still is an important test of lepton flavor universality violation. And so the idea is to see what the CPC could do for ratios of this kind, okay? But also involving different final states. So always of the kind B2 charm, tau nu, but with J psi, D sub S, and so on. And the outcome is always that they could reach order % level precision. Again, these are estimates based on statistics only, but at least these are ratios of branching ratios. So most of the systematics hopefully should drop. And basically one of the last topics is again lepton flavor universality test. Because if you really believe there is something, some new physics there, and you fix it basically with an operator involving only 3rd generation fermions, and then you rotate basically this top to a charm with a CKM. Anyway, you can close the loop, attach a W, and you also induce lepton flavor universality violation in purely leptonic decays. Okay, this is an old story. So models of this kind to address RD star are typically to some extent or strongly constrained by lepton flavor universality test in tau decays. So this is something that you really need a high energy heterogeneity factory basically to improve the test. Because as you know, in the standard model, what you have is this, okay? So W exchange that induce the muon, the standard muon decay, and the leptonic decays to the tau. Well, not only the leptonic decays, but in this case, I will focus on the leptonic ones. And of course, these couplings are all the same in the standard model, just SU2. But if you are an experimentalist, you want to test that, right? You want to check whether they are indeed the same numbers. So to do that, you basically build these ratios here, which then will depend on ratios of the branching of these branching ratios times some corrections due to phase space and radiative corrections, basically. Okay. So in particular, you see this one that test the ratio. Of course, the standard model prediction is 1, right? The test between the coupling to tau and the coupling to lighter generation depends on branching ratios, masses, and lifetime of tau and muon. Okay, but the muon decay, we know it very well. The muon mass, we know it very well, and the muon lifetime. So the uncertainties only comes from these measurements of the properties of the tau. Okay, tau lifetime, tau mass, and the leptonic branching ratios of tau. So the current status is this one. So everything is beautifully consistent with standard model with uncertainties at the per mil level, okay? And the uncertainties come basically mostly from the knowledge of the branching ratio that we know mostly from lab with the recent contribution from Bell 2, okay? And similarly on the lifetime, still at the per mil level, while for the moment the mass of the tau gives the contribution to the uncertainties that are below the per mil level. So this is something you can do better at low energy. So BESS3, BEL2, if we will ever build a super tau-chan factory, can improve on this. But to improve on the branching ratios and the lifetime, it's better to use a high energy machine, okay? So, okay, this is the current situation. So so you see here you have three parameters. You can plot two. So this is the standard model prediction. This is the measurement. Is within uncertainties compatible with the standard model. If you have some new physics that couple to third generation, like an operator like this, would give you a deviation only to the coupling to tau of this kind. So this tells you that this constraint here basically translate to a bound on the scale of this operator order 10 TeV. If you go to high energy, to a Tera Z machine, you can hope to, of course, all these measurements are purely systematic dominated, but people are estimating that you can go from these per mil level predecisions to, well, something like 1 order of magnitude improvement, okay? So which means that from this current precision, you would shrink to this little blue dot, okay? So of course, the central value, we don't know where it is, but this shows that the test, the lepton flow universality test would become a much more stringent. Which then we would increase this test on a new physics operator up to order 20 TeV or something. Last thing is something similar to what I discussed last week. If you have something light, or also what we mentioned before, if you have some light new boson, like an axion-like particle, and the tau decays into it, okay? So like tau to mu plus something invisible. The present bound is very recent from Bell 2. It's a difficult thing because you have this invisible object. The present bounds on the branching ratio are just order a few times 10 to the minus 4. And you can try to search for this also in this kind of environment. And the estimate, preliminary estimate, is that you can go below order 10 to the minus 6 in the branching ratio. Okay, so this then would test, if you want, the decay constant of this axion-like particle at the level of 10 to the 6, 10 to the 7 GeV or something like this. So if you go to look at the paper, there is all a list of benchmarks that can be searched and different degrees of how reliable, some guess estimate, some fast simulation, some full simulation, and so on. There are more than 40. There are, yeah, also things that you can do beyond the z-pole. So Higgs decays, tau decays, and so on. Didn't have time to mention. So I just conclude. Simply, I wanted just to remind you that, I mean, the flavor sector of the standard model is quite mysterious and interesting in itself. So it's not impossible to learn something from it, okay? And flavor observables are the natural playground to test energies that are, well, among the largest that you can really access at a laboratory experiment. To be concrete, I gave you this example of this CPC white paper, so of the flavor opportunities you have there. And well, the nice thing is that with 10 to the 12 ZDKs, you can study things that you cannot do as well, okay? So there are plenty of opportunities. So if I can joke around the title of this conference, I would say that, well, one way to reach high energies with colliders is use colliders to do flavor physics. Thank you.
Thank you. Any question, comment, complaint?
Given the measurement from the lepton flavor violation, what can we get? What information can we get from about the UV model? How to distinguish different flavor models? Because it's very complicated.
From the ZDK?
I see.
Yeah, no, I mean, which lepton flavor violation you mean? This one, the lepton flavor violation in ZDKs? Or, so you're asking about this?
I mean, you get many sensitivity to the variation coefficients, right?
Exactly.
So
basically,
what information can we get about the UV model?
this is the usual problem. So basically, you are sensitive only to these coefficients here. Dipole operators, but these are already constrained by tau mu gamma and so on. So basically, you can have a large deviation in these Z decays and not, for instance, in tau decays, if your new physics, for some reason, mostly gives you these lepton Higgs operators, lepton Higgs currents. Then if you're asking me what UV completion would give you this and not just a 4 fermion operator, well, and also a 4 fermion operator, probably there is none, or there is no reasonable one. Anyway, you need this kind of things to induce lepton flavor.
Can we know something about the flavor pattern? You have mentioned in the beginning of your talk, you have many flavor patterns, the broken symmetries, many kinds of broken symmetries.
Well, that's also a possibility. You may have flavor symmetries that basically gives you sort of selection rules. So do not allow to write certain flavor combination for certain operators. And do not suppress this instead. But I don't have any UV completion in mind.
Okay.
Can you show again the with the many Z final states next to last maybe?
What do you mean?
Yeah,
the Z decays?
Yeah, the one, for instance, J psi gamma. So, next.
So
Excellent.
this stuff here,
Yes.
the summary tables,
Okay. So I just wanted to understand if in the context of CPC, they studied three-body decays, or they decided not to, or they decided that they were not worth to be studied. Because
What-
I know in FCC, for instance, they started to do this kind of studies.
but three-body decays, I mean,
No, of the Z, of the Z.
um,
Spions, which
Yeah.
that's the one that caught my eye when you were saying.
yeah.
In general, I see that they are trying to make ultra rare Z three bodies,
Right.
which my personal opinion is just that it's stamp collection.
I think you learn some QCD here, but I don't know what kind of new physics would give you this.
Exactly, and the motivation is a bit weak. So I noticed that you have a very recent result and you're not including them. Instead,
But you say this
they
is
decided to add
really-
this very last minute.
it's really a very naive estimate. I don't think it's
Yeah, but
any real simulation.
whoever made this table made a choice of what to, whoever made the table made a choice of what to study and put on the table. I'm just remarking that the friendly competition from Geneva has a much longer table that shows lots of results, many of which are on multi-bodies, which are cool, but not necessarily my opinion. So I wanted to understand if this was considered and not included, because these multi-body things are
Simply we didn't have any actual simulation or any actual study on that. Somebody wrote a small paragraph mentioning this and why it could be interested. You can go and have a look at it. But yeah, nobody had really time to invest in
Okay.
that. And that's it.
So it's
They
whatever
may
came
prefer
out.
to do something else.
that-
So maybe it's a sociological question.
Vabbè, te lo dico dopo.
I think it's a usual story. When you add a particle in the final state or two, you need to either increase the dimension of the operator that you're testing, and then the bound becomes usually worse. No, always worse. Yeah.
Definitely. Now, for sure, somebody in the long list of the collaborators think that they are useful, but they didn't have time to work on that.
Hi, I have a naive question. So in your previous slide, mentioned the FN flavor model, the Froget
Froget-Nielsen, yeah.
flavor model. Yeah, yeah, this one. So this is when the energy scale is lower than lambda, then we have this high dimensional operator, right?
Right.
And they satisfy the U1 global symmetry. So if the energy, if we are in the UV scale larger than lambda, do we still have the term satisfy this U1 symmetry? Can we write such UV theory?
Well, I don't know if I understand what you mean. So, well, simply the idea here is that at the scale lambda, you have new states, new fields, and the symmetry is unbroken, okay? So you can only write, for instance, if it is a U1, okay, U1 invariant terms, but then you have a scalar that is charged under this U1, takes a VEV and breaks it. And the VEV is somehow a little bit smaller than this cutoff scale. So you can write these operators, but in terms of this ratio here, which is
but all those are high dimensional operator, right? Larger. Now we know
right.
that.
You will have a higher dimensional operators that, they are further suppressed. So these are the leading contributors.
Yeah, so above the energy scale, above the lambda scale, this operator must come from a renormalizable operator.
Yeah, exactly.
Yeah. So can we write renormalizable operator which also still satisfies this U1 symmetry?
Yeah, sure. But you need to introduce new fields. Okay. So you need the new degrees of freedom at the scale lambda. Either basically you have to open this block. So either heavy fermions or heavy scalars.
Oh, okay. Thank you.
We call it a day. Time for dinner. So dinner, which is
So everybody should have received another mail, again, with the same link. So if you didn't get it, either because I sent it, or either went in spam or whatever, but let's thank Lorenzo, no?